Hi everyone. Okay, this is the last video in this little introduction to abstract algebra and groups. This is just an example. I work out the dihedral group of order 6.
Okay, the last one that I want to look at is a group with 6 elements. So there are, just like with 4 elements, there are 2 possibilities. I'm not going to go through one, but one is just another cyclical clock group. So just goes around like that, 0, 1, 2, 3, 4, 5. Then the other one is what is called D3. D stands for dihedral group. And this is the first group that is not commutative. It's the smallest group that we can find, that we can make, that is not commutative. So the way it works is it's basically the rotations and the rotations and the flips that you can do to a triangle. So I have my little visual aid here. So you can either leave it the same, that would be the identity element. You can rotate it 120 degrees, or rotate it 240 degrees, or you can flip it on any one of the axes from the point to the opposite side. So this is one flip, this is one flip, and this is one flip. So we'll make the table. So we have a rotation of 0, rotation of 120, rotation of 240, and then a flip, 3 flips. Flip 1, 2, and I'll just label them. The flip around the T is F1. The flip around the R is F2. And the flip around the L is F3. So, and then, so we have R0, R120, R240, F1, F2, F3. So let's just see what we get here. Oh, whoops. I made a mistake. I need one more row here. So we'll just call that star. But so the important thing to understand when you're looking at this, if you want to do this yourself, is that the elements of this table are the action itself. So the binary operation is actually a combination of the two. You rotate it 120 and then you rotate it 120 again. So the elements are not the position of this triangle. The elements are the rotation. So one element is doing this, one element is doing this, and so on. And then so the question is, what happens if we do them together? If we compose them, one and then the other, we're going to end up with one of these 6 rotations, as though we did it directly. So for instance, this again is the identity. So you can see if we start by doing nothing and then we rotate it 120, that's the same as if we just rotated it 120. Okay, so that's that. If we do nothing and then rotate 240, do nothing, rotate 240, and this is the same as just rotating 240. So that's our 240. And then we can quickly fill in the rest. These are very easy to do. So if you rotate it one turn and then rotate it another turn, that's obviously R240. And if you rotate it 1 and then rotate it 2, you're going to end up back where you started. So that's 0. If you rotate it twice and then rotate it once more, you're going to be at 0. And if you rotate it twice and then rotate it twice again, you're going to end up having gone around once. So you go around twice again, and you'll end up over 1. So this is basically like a subgroup, actually. These also form a group of order 3, right? It would be like just having 0, 1, and 2 here in your cyclic group. So what if we do a rotation and then a flip? So if the first one, obviously this again is just the identity element, so we know that these are F1, F2, F3. We also did the same thing here. What if we do a real one now? So we start like this. So we rotate 120, and then we flip. Now, one really important thing to remember if you're trying to do this yourself is that this translation is always the same, no matter the position of the triangle. So if you rotate 120, and then you're flipping from the top, you're not flipping from the top of where it is now. You're flipping the same, you're doing the same translation. The translation is basically keep the T the same and flip the L and the R. So that's what this really means. So the first rotation means move this here, this here, this here. And then the second rotation means keep the T where it is and change the R and the L. So then you just ask yourself, what does that give us? That is the same as if we had held the L straight and flipped the R and the T, right? If we started here and just did this, that's what we would end up with. So keeping the L straight, flipping around the L is F3. So so starting with the rotation and then doing F1 leaves you with F3. So if we rotate once and then flip around the R, then in that case, the T stayed the same and we flipped around the T, so that's F1. So this one has to be F2. Let's check it. If you rotate and then flip around the L, you end up with the R staying straight, flipping these two, so that's the F2. Okay, and the next one. So we start by rotating 240, and then again we flip around the T, and what do we have? The R stood still, and we flipped the T and the L. That is F2. And we can now figure this out because there has to be an F3 and there has to be an F1. So if we rotate 240 and then flip around the R, we end up with the L staying still and flipping the R and the T. That's F. Whoop, did I mess something up? No, what am I doing wrong? Go 240 and then flip around the L. Oh, right, and then you have the T at the top. I don't know what I did wrong. Okay, so we got it. Okay, now let's fill in this section. So in this case, now we're going to start by flipping first and then rotating 120. Now, it's super important to remember the same thing that I said about the flipping counts here too. This can be very confusing. You have to keep it straight. You flipped, but now the rotation, what the rotation 120 actually means is T goes to R goes to L goes to T, okay? So if we turn it around, we're actually rotating in the other direction because this actually isn't a rotation of what we're looking at. It's actually the translation of T to R to L, and L to T. So we flip and then we rotate it this way, which will give us, the R didn't move, this is an F2. And then if we do it again, flip once, and then rotate 240, so it would be back this way. Here the L didn't move, these moved, that's F3. Okay? So, how do we get, okay. One more time. So, for F2, flip it around the R, and then rotate it 120. And in this case, the L stood still, these two flipped, that's F3. One more, we know it's going to be F1, let's test it. So we do the F2, rotate it 240, and it looks like the t stood still and these flipped. That's F1, right? That's what we wanted. Okay, finally the F3. The F3 is a flip around the L, and then we rotate 240, which is counterclockwise twice. And in this case, the R stood still, these flipped. So, do I have that right? We're on, nope, I got something wrong. Let's make sure. Because we know now this is going to be F1. So what did I do wrong? Flip around the L, flip around the L, and then rotate, oh, we were on 120, that was why. Rotate counterclockwise 120, and now we have the R staying still and the T and L flipped. That's, no, I'm sorry. We have the T standing still, these flipped. That's F1. The final one's going to be F2. Now we're going to do the 240. So we flip around the L, and then flip, rotate it clockwise 240. And here the R stayed still, that's F2, which is what we wanted. Okay, now this is interesting because now we're doing flips and then flips, and we're gonna end up with rotations because we're turning it over twice, right? So the first one, so 3 of these are gonna be obvious. Flip it once, flip it again, and you're gonna have R0. We can guess, flip F2, flip it again, we're gonna have R0. And same for F3. Flip it once, flip it again, and we have our 0. Now, let's flip the T, and then you flip the R. And what is that? That is a 120 rotation. That's R120. And if we flip the T, and then flip the L, that is a 240 rotation. Okay. So again, we can fill it in from here just about, I think so. But let's just do a couple more. So if we flip it around the R and then flip it around the T, what do we have? We have a 240, which it has to be because it can't be that one. So this has to be 120. So flip it around the R, and then flip it around the L, and what do we get? We got a 120. Okay, last time. Flip it around the L, flip it around the T, and we have a 120, which is what it has to be. And then this has to be 240. Just for completeness, flip it around the L, and then flip it around the R, and that's 240. So, okay, there we go. So this is the D3 group, and the interesting thing is that for the first time, it is not symmetric. It's symmetric here. This part's symmetric. If you just do the rotations, they're symmetric. You have 240, 240, 120, and these are not symmetric. Even though the F1s are going down here through the middle, F2 and F3, they're flipped. So there are symmetries here, but it's not symmetric across the diagonal. Which I'm only looking at the subgroup here anyway. The real question is this a mirror image of this? But you can see that it's not because it's F2, F3, F1, F3, there's F3, and then these two are both F2, but these are something else, those are something else. But here, this part is symmetric, right? 1, 1, 2, 2, and all threes. And here we have the identity down the middle, but this again is not symmetric because it's 240. So overall, this whole group, it's the first group that is not commutative. So that's interesting, and that's the end for that we're going to look at for finite groups.
I just want to add a few more comments here about the group we were just looking at, the dihedral group of order 6, which is referred to as D3. The really interesting thing is that there is another kind of groups called permutation groups, which the dihedral group is an example of it. It is rotations and reflections of a polygon. The one we looked at is a triangle, but there's a similar group for squares, etc., every polygon. But there's another group called a symmetry group, which is the set of permutations of a group. Now, it's looked at in a completely different way from thinking about it in terms of rotations and flips of a polygon, but it is actually isomorphic. So the group D3 is isomorphic to the group S3, which is the symmetry group for three elements. So we haven't looked at what isomorphic means. It basically means that the two structures, their structure is the same. So it's not just a set has similar elements, but also whatever structure's been imposed are equivalent for the two. So D3 is just another way of describing S3. We'll look at isomorphisms more at some point. So in S3, we have, these are the 6 elements. And you can see here, so you start with a group, or with a set with 3 elements, and then you, what's the word, permutate? The elements. So for P0, it's the identity element. You start with P with 1, 2, 3, you end with 1, 2, 3. Then P1, you move everyone down, you move everyone 1 to the left. So 1 becomes 2, 2 becomes 3, 3 becomes 1. Row, I said P, but it's row. Row 2, then you move it twice. So 1 becomes 3, 2 becomes 1, 3 becomes 2. And if you think about it, this is exactly what we did with the triangle, right? This is a rotation of 120 degrees. 1 became 2, 2 became 3, 3 became 1, and row 2 then is the same as rotating 240 degrees. So 1 becomes 3, 2 becomes back to 1, and then 3 becomes 2. So these are just like the rotations in the dihedral group. And then the mu's are the same as the flips. So for mu0, we leave the first element alone and we just flip 2 elements. That's just like taking a triangle and flipping it over. So one vertex stays where it is, the other 2 flip. So then mu1 keeps position 2 where it is and flips 1 and 3, and then mu2 keeps position 3. Oh, you know what? I labeled those wrong, didn't I? They should be, they should be 1, 2, and 3. It's a little less confusing. So mu1 keeps 1 straight, mu2 keeps 2 straight, and mu3 keeps 3 straight. So here is the table. This is called a Cayley table, by the way. Cayley. It's a Cayley table. The Cayley table, or the multiplication table for this symmetry group, if you look at this, it looks exactly like the dihedral group we just did. The 3 rotations here, down here, the identity is right down the middle. Here, the identity is right down the middle. Here, it's in position 1, 3, and 2, 1, 3, and 2. The 3's go across there, the 2's go across there. This is exactly what we just finished drawing for the dihedral group. But here, it's just thought of as a permutation group. These permutations and this notation is vital, again, to Galois theory, where if he looks at roots of an equation, so if you have, say, the square root of 5, if you square the square root of 5, you come back to 5, right? So you start in the, say, the rational numbers, you multiply by the square root of 5, and then you're into a field that has added the square root of 5. And then if you square that again, you're going to go back into the original field. So if a polynomial has multiple roots that are all irrational, then they will in some way behave in the way that we're looking at here. So if it was a cubed root, then it would actually be, it would take 3 times to get back into the rationals. So all that's very vague. We'll have to talk about that more later when we get into Galois. But I just wanted to point out that these triangles are interesting in themselves, but also these permutation groups, the symmetry groups, are very important for Galois. And to say it again, Galois is very important for the proof of Fermat's last theorem and the elliptical group law. Okay, that is it for this example. Okay, that's it. That's the last video we're going to do for this little introduction to abstract algebra and groups. As you can tell, there's way more to talk about for groups, but this gives you a thorough introduction to what we're talking about when we talk about the group law for elliptic curves, which is what we need to know to go forward. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.